today's session we will look at what is called as a Hilbert transform. So far we have seen Fourier transforms. What is the purpose of using a Fourier transform? The Fourier transform we have used to change the time domain representation of a signal into a frequency domain signal. Basically, we have applied the Fourier transform in majority or most of the cases they have been applied to energy signals, and in some cases also we have applied this Fourier transforms to power signals. When I apply a Fourier transform to a signal, basically we will get different components of that signal. That means a time domain signal has been converted into a frequency component called as a frequency spectrum. Now, what is the use of converting a time domain signal into a frequency domain signal? When I take a Fourier transform of a signal, what we can do is basically we can select frequency components which we want and reject frequency components which we do not want. That means I can do what is called as a filtering on the basis of the frequency components generated from a time based signal, and then filtering out to get what frequency components I need. So, if you see here, I have a time domain signal. Okay, this is a time domain signal. We apply a Fourier transform to it. Then what I will get is, I will get a frequency components or a frequency domain signal. When I say frequency domain signal, it means I have a frequency, then we can have different frequency components like this. So, these are different frequency components which we get from a time signal. In this, let us say I want to select only these two frequencies, this band of frequencies. Then I do what is called as a filtration. Frequency selection is being done, and then we do filtration to pick up only these components. This is the basic functionality of a Fourier transform. Okay, that means in selection of signals, what I will do is, one method is getting its frequency. Okay. So, that means I want to select a particular batch of signals, then I will get a frequency domain representation of the signals, then I will, based on the frequency, we will select them. That is one. The second one is what is called as a phase selection. Okay, we do what is called as a phase. That means if I can distinguish the different components of a signal by phase, that means if each and every component is varied by a certain phase, let us say 180 degrees, which is very common. That means all components of the signal are shifted by 180 degrees. That is, there is a phase reversal. So, as you all aware, this type of phase reversal happens in the case of an ideal transformer. So, what does an ideal transformer do? The transformer takes the input of a signal and then converts each and every component of the input signal by shifting it 180 degrees. That means there is a phase reversal. Similarly, there is another case here where I will shift the signal by plus or minus 90 degrees. That means each and every component of the signal is shifted by plus or minus 90 degrees. That means instead of 180 degrees, I am shifting a signal by plus or minus 90 degrees. When I do this, this is done by a transformer called as a Hilbert transformer. So, we will use that Hilbert transformer here. Okay. Now, let us understand in detail in this session what is a Hilbert transform, how does it work. But basically, the basic understanding is the selection of signals can be done using frequency selection. So, we use Fourier transform for that. Phase selection can be done by 180 degrees change, phase reversal of 180 degrees, that is phase inversion, that is signal is completely inverted, that is done by using ideal transformer, and then I can have plus or minus 90 degrees phase shift, then this is called as a Hilbert transformer. Now, in this session we will concentrate on what is a Hilbert transform, what is the relation between a Hilbert transform and a Fourier transform, and we will see some examples highlighting the importance of a Hilbert transformer. Hilbert transform. Fourier, Laplace and Z transforms change from the time domain representation of a signal to the frequency domain representation of the signal. So basically when you talk about a Fourier transforms, Z transforms and S transforms, the basic fundamental transformation that is happening is there is a change from the input representation. That is, if input is in time domain representation, we are completely transforming it into a separate domain, that is a frequency domain. Now, the resulting two signals are equivalent representations of the same signal in terms of time or frequency. That means there is no change, isn't it? So, the same signal we are representing in two ways. That means, if the signal is represented in the time domain, then we are also representing in the frequency domain. Thus, there is no change in the signal. The signal is same, whereas the domain representation has changed. Okay? So, in contrast, the Hilbert transform does not involve a change of domain, unlike many other transforms. So, the major difference between Hilbert transform and other transforms is that in Hilbert transform, there is no change in domain. For example, Hilbert transform is in the time domain only, but it is a complete different representation of the signal that is given to it as input. So, that is a Hilbert transform. Okay, so Hilbert transform is basically an auto transform, but it does the following things. The result of a Hilbert transform is not equivalent to the original signal, rather it is a completely different signal. That means, whereas we are representing the same signal in different domains, in a Hilbert transform, as you have seen earlier, there is a phase shift of 90 degrees of the signal, plus or minus 90 signals. That means there is a complete change in the input signal. Okay. Second, the Hilbert transform does not involve a domain change. That is, the Hilbert transform of a signal x of t is another signal denoted by x cap of t in the same domain, that is time domain. So, let us see. So, what is the Hilbert transform doing? It is not involving a time domain change. That means, if I am representing in time domain, the signal essentially remains in time domain only after Hilbert transformation is done. So, x of t is changed into a completely different format signal, which we call it as x cap of t. So, here x cap, the cap indicates Hilbert transform. The most significant point we should all understand is x of t is transformed into x cap of t. T. So, time domain representation is also, the output is also a time domain representation in the case of a Hilbert transform. That is the most important point we should remember. But it is changed. X of t is changed into x cap of t, that is the Hilbert transform. So, let us see the next slide. The Hilbert transform of a signal x of t is a signal x cap of t whose frequency components lag the frequency components of x of t by 90 degrees. So, the Hilbert transform of a signal x of t is a signal x cap of t. That means we are representing Hilbert transform as x cap of t. So, x cap of t is whose frequency components lag the frequency components of the input signal of x of t by 90 degrees. So, x cap of t has exactly the same frequency components present in x of t with the same amplitude, except there is a 90 degrees phase delay. So, x cap of t has exactly the same frequency components present in x of t with the same amplitude. The amplitude is also not changing, but what is the difference? There is a phase lag of 90 degrees when I take the output of a Hilbert transform. That means the Hilbert transform of, let us say, example x of t is equal to a cos 2 pi f naught t plus theta is a cos 2 pi f naught t plus theta minus 90 degrees, that is a sin 2 pi f naught t plus theta. That means a cosine function with certain phase lag, when it passes through a Hilbert transform, there will be a phase lag of 90 degrees added and the resulting will be a sine function. So, this is the Hilbert transform. So, basically what is that Hilbert transform doing? Hilbert transform is represented by letter called as x cap of t. Okay. So, all the frequency components are shifted by a phase lag of 90 degrees in the case of x of t. So, when I pass a cosine signal to the Hilbert transform with a certain phase angle of theta, when it passes through a Hilbert transform, the output will be a sine function because of the phase lag of 90 degrees. A Hilbert transform adds a delay of pi by 2 at all frequencies. That means e to the power of j 2 pi f naught 2 will become e to the power of j 2 pi f naught t minus pi by 2. That is minus j e to the power of j 2 pi f naught t. Similarly, e to the power of minus j 2 pi f naught t will become e to the power of minus j 2 pi f naught t minus pi by 2 is equal to j e to the power of 2 pi f naught t. That means At positive frequencies, the spectrum of the signal is multiplied by a factor minus j. Negative frequencies, it is multiplied by plus j. Now, what is happening here? When I add a delay of pi by 2 to all frequencies, essentially it has two cases here. One is a case where exponential j to pi f naught t, and the other case is e to the power of minus j to pi f naught t. When it is e to the power of j to pi f naught t, it will become e to the power of j to pi f naught t minus pi by 2, that is minus j e to the power of j to pi f naught t. If it is e to the power of minus j to pi f naught t, it will become j e to the power of j to pi f t. That means essentially all positive frequency components are multiplied by a factor of minus j, and all negative frequency components are multiplied by a factor j. The spectrum we are multiplying by minus j and plus j for positive frequencies and negative frequencies respectively. In other words, it is equal to multiplying the Fourier spectrum by a factor of minus j signum of f. So, this is how we calculate the Hilbert transform. So, this is equivalent to saying that the spectrum Fourier transform for signal is multiplied by minus j signum of f. So, we have put it here for you. So, it says that x of t is real, of course, and has no DC component, that is x of f at f is 0 is equal to 0. Then the Fourier transform of Hilbert function is equal to minus j signum of f x of f. So, we know that the Fourier inverse transform of minus j signum of f is 1 by pi t. Therefore, x cap of t can be calculated as follows. It is a convolution of 1 by pi t and x of t, that is 1 by pi integral minus into plus infinity x of tau t minus tau d tau. The operation of the Hilbert transform is equivalent to convolution, that is filtering. So, there are two formulas separately here. X of t you have to calculate separately, that means x cap of t, if given x of t, x cap of t is equal to 1 by pi t convolved with x of t, that is equal to minus infinity plus infinity x of tau by t minus tau d tau. Or if I can find out the Fourier transform of the given signal x of t, then I multiply it with minus j signum of f, I will get the Hilbert transform x of t, that is Fourier transform of x of t, that is I will get the x cap of f, that is nothing but our Hilbert transform in frequency domain. Okay, so let us just see this, write these two formula on the board. X cap of t is given by 1 by pi minus infinity plus infinity x of tau t minus tau d tau. Okay, and then Fourier transform of x cap of t will be equal to minus j signum of f into x of f. Okay, so these are the two formulas you should remember here. Okay, x cap of t is minus j signum of f x of f. So, there are two ways of doing this. One, if I know x of t, I will find out the Fourier transform of it, x of f. This is one way of doing. Then after I get x of f, I multiply it with minus j signum of f. So, when I do this, I will get a Fourier transform of x cap of t. That is what we have written. So, there are two ways in which you can solve the problem. The one is this very complicated problem. In fact, this is the convolution of 1 by pi t and the x of t. Okay, this is nothing but convolution of 1 by pi t convolved with x of t. Okay, this seems to be the first formula seems to be a little bit complicated, otherwise it takes a little bit of more time. So, the most preferred method here is take the Fourier transform of x of t, then multiply it with by minus j signum of f, then you will get x cap of f, then that you take the Fourier inverse transform of it, you will get the Hilbert transform. So, this is the second method is comparatively easier than the first method. So, I will read this again. F of x cap of t is equal to minus j signum of f x of f. This is one way of getting. The second is x cap of t can be obtained by convolving 1 by pi t with x of t. That will be equal to 1 by pi integral minus into plus infinity x of tau by t minus tau d tau. Performing the Hilbert transform signal is equal to a 90 degrees phase shift in all its frequency components. Therefore, the only change the Hilbert transform performs in a signal is changing its phase. The amplitude of the frequency components of the signal do not change by performing the Hilbert transform. On the other hand, since performing the Hilbert transform changes cosines into sines, Hilbert transform S cap t of a signal x of t is orthogonal to x of t. Also, since Hilbert transform introduces 90 degrees phase shift, carrying it out twice causes a 180 degrees phase shift, which can cause a sign reversal of the original signals. So basically, what does a Hilbert transform do? Hilbert transform basically changes the phase of the all components of the signal given to it, and there is no variation in the amplitude. The only change that is happening is there is a phase difference of 90 degrees that is being added. The amplitudes are not changed. Finally, if I apply Hilbert transform 2 times, then I will get a phase reversal of 180 degrees. So this is these are some of the essential points of a Hilbert transform. And also, if I apply a cosine function to Hilbert transform, I will get a sine function. In other words, the Hilbert transform is orthogonal. X cap of t of a signal x of t is orthogonal. Now look at some of the properties of Hilbert transform. The first property is evenness or oddness. The Hilbert transform of an even signal is odd, and the Hilbert transform of an odd signal is even. It's very easy to remember. Okay, the Hilbert transform of an even signal is odd, and the Hilbert transform of an odd signal is even. This is possible because we are adding a phase lag of 90 degrees. Proof. Let us see the proof. Just it is a logical proof. If x of t is even, then of course x of f is real and an even function. Okay, then to get Hilbert transform, I should multiply this x of f by minus j signum of f. So when I do that, minus j signum of f x of f is an imaginary, because you are adding a j there, and is an odd function. Hence, its inverse Fourier transform x cap of t will be odd. So what is the proof? What are we doing here? We take an even function, then we are calculating x of f, which is also even. Then when I multiply x of f by minus j signum of f, x of f, the result is imaginary and odd. So we are given an even signal, and the Hilbert transform what we got is an odd signal. Okay. Similarly, if x of t is odd, then x of f is imaginary and odd. Thus minus j signum of f, x of f is real and even. Therefore, x cap of t is even. So we should remember this: when x of t is even, x cap of t is odd signal, and if x of t is an odd signal, then x cap of t, that is a Hilbert transform x of t of an odd signal, is an even signal. Another property is sign reversal. Applying the Hilbert transform operation to a signal twice causes a sign reversal of the signal. That is, x cap of t will give me minus x of t. The proof is here. Okay, the proof is like this. We are calculating the Fourier transform of x cap of t. Okay, so we know is equal to minus j signum of f x of f, isn't it? So this will be a multiplication of minus j signum of f whole square x of f. Okay, so this is equal to minus x of f. So this is proved. Okay, so this is proved. Now sign reversal, applying the Hilbert transform operation to a signal twice causes a sign reversal of the signal. That is, x cap of t twice. That means x cap of t, then x cap of t. That means you are taking Hilbert transform twice, will give me a signal that is minus x of t. Of course, because 90 degrees and 90 degrees will give me a 180 degrees, that there will be a reversal in the signal sign itself, isn't it? So we will get an inverse signal, that is minus x of t. So what is the proof here? The proof we have seen on the board also. Now I am also just reading it for you. The Fourier transform of x cap of t is minus j signum of f whole square x of f. This will be equal to minus x of f. Okay, so x of f does not contain any impulses at the origin. This is a very important point we should remember. X of f does not contain any impulses at the origin. Let's see the other property, energy. The energy content of a signal is equal to the energy content of its Hilbert transform. Okay, the energy content of a signal is equal to the energy content of its Hilbert transform. Okay, that means the energy present in a signal is equal to the energy present in a Hilbert transformed signal, right? So proof, what is the proof here? Let us see Rayleigh's theorem of the Fourier transform, which says energy of a signal is given by minus infinity plus infinity x of t whole square dt, that is equal to again minus infinity plus infinity x of f mod whole square df. When I take the Hilbert transform, energy of the Hilbert transform signal, it will be minus infinity plus infinity x cap of t whole square dt, that is equal to minus infinity plus infinity minus j signum of f x of f whole square df, that is simply equal to minus infinity plus infinity x mod x of f whole square df, because the fact minus j signum of f whole square is equal to 1 except at f is equal to 0, and the fact that x of f does not contain any impulse at the origin completes the proof. Let us see this proof on the board. Let us see this. What is the energy of a signal? Let us say we are calculating the energy of a signal x, that is given by the famous formula minus infinity plus of infinity x of t whole square dt. As you all know, using Rayleigh's theorem, this is equal to minus infinity plus infinity x of f whole square df. Okay, so this is a Rayleigh's theorem. Now I want to know what is the energy of a signal, which is the Hilbert transform. So I applied a Hilbert transform, what should be it? So then it will be like this, minus infinity plus infinity x cap of t whole square mod of that whole square dt. Now what is x cap of t in terms of frequency? We have seen earlier that Fourier transform of x cap of t is equal to minus j signum of f x of f, isn't it? So we put it here. So that will be equal to minus infinity plus infinity minus j signum of f x of f df. Okay, if you look at this, this square of this is 1. So I will get an answer that is equal to minus infinity to plus infinity x of f whole square df. So this and this is the same. That means the energy content of a signal x of t is this, and the energy content of the Hilbert transform of the signal is again this. That means the energy content is same in both cases, thus the proof. Let us see the other property of Hilbert transform, orthogonality. The signal x of t and its Hilbert transform are orthogonal. Proof. Let us take Parseval's theorem of the Fourier transform and we get this. So apply Parseval's theorem. As you see here, I am doing minus infinity plus infinity x of t x cap star of t dt, then that will be equal to minus infinity plus infinity x of f minus j signum of f x of f star df. So that will be equal to 0. Here we have used the fact that x of f is Hermitian and x of f whole square is even. Let us see an ideal filters now briefly. What is an ideal low pass filter? It is an LTS system, linear time invariant system, that can pass all frequencies less than some w and reject all frequencies beyond w. Okay, here you see this low pass filter. This is the characteristics. That means no frequencies below minus w and above w are allowed. So this is why this is called as a low pass filter. Then you can have an ideal filter, which is a high pass filter, ideal high pass filter. In ideal high pass filter, there is unity outside the interval minus w less than or equal to f less than or equal to w and 0 inside. It means so called certain low frequency components are being eliminated. So we are looking at components beyond it. So that is an ideal high pass filter. Okay, we are calling it ideal high pass filter because the gain seems to be completely uniform throughout. Then you can have a band pass filter. If you see here, it can have a frequency response that is unity in some intervals and 0 otherwise. That is why this is called as a band pass filter, and the bandwidth of the filter is given by W2 minus W1. So that is the bandwidth of it. This is an ideal band pass filter. Then you can have what is called as a non-ideal filters. If you look at the ideal filters, the gain is uniform. That means we are able to select the particular frequencies exactly. But whereas that's not the case, non-ideal filters where you have a 3 dB bandwidth instead of a regular bandwidth that is equal to W2 minus W1. Here you see, for non-ideal filters, the bandwidth is usually defined as the band of frequencies at which the power of the filter is at least half of the maximum power. So if you see here, for non-ideal filters, the bandwidth is usually defined as the band of frequencies at which the power of the filter is at least half of the maximum power. This bandwidth is usually called the 3 dB bandwidth of the filter, because reducing the power by a factor of 2 is equal to decreasing it by 3 dB in the logarithmic scale. So, you can see some filters with a 3 dB bandwidth which are shown here. The low pass and band pass signals. Low pass signal is a signal in which the spectrum, that is the frequency content of the signal, is located around the 0 frequency. That is a low pass signal. That means the frequency components which are nearer to 0. This is called as a low pass filtering. What is the band pass signal? Band pass signal is a signal with a spectrum far from the 0 frequency. That is one. The frequency spectrum of a band pass signal is usually located around a frequency Fc, where Fc is much higher than the bandwidth of the signal. So, band pass filter is, we have a certain band of frequencies located around a certain frequency, let us say Fc. So, Fc is generally very greater than 0, whereas low pass filter, the whole band of signals exist, or the spectrum of signals exist around 0, whereas in a band pass filter, the frequency components are located at plus or minus Fc. So, this Fc is supposed to be very greater than 0, and in fact, in most of the cases, this is Fc is beyond the bandwidth of the signal also. So, if I have signals existing at plus Fc here and minus Fc here, where Fc is greater than 0, very much greater than 0, then it becomes a band pass signal. Let us see an example on Hilbert transform. Okay. Example, find the Hilbert transform of x of t is equal to cos 2 pi fct. Okay. That means we should find out what is x cap of t. Okay. There are two ways of doing this, and the most common method I told you is, first I have to calculate, the first step is get x of f, then multiply x of f by j signum of f. Okay, do this. Then third step is find the inverse Fourier transform, okay, of x of f. Okay, this is x cap of f which you will get, then you will get a x cap of t. So, these are three steps. First find out x of f, then minus j signum of x of f will give you x cap of f. So, this will give you the x cap of f, then comes the inverse term, then you find the inverse Fourier transform, then you will get this. Otherwise, we know the famous formula where you have to convolve 1 by pi t with x of t, that is 1 by pi integral minus into plus infinity x of tau by t minus tau d tau. So, that appears to be really complicated. So, let us follow these steps. Okay. Now, as per this, first job of mine is to find out what is x of f. If you remember, in our earlier sessions we have calculated cos 2 pi fct Fourier transform. What was it equal to? It was equal to two delta functions existing at plus or minus fc with a scaling factor of half. So, this is equal to half of delta f minus fc plus delta f plus fc. Okay. Now, we got this. So, this is x of f. Now, what is it I have to do? To find out the Fourier transform of x cap of t, I should multiply this by minus j signum of f x of. So, what I will do is, now let us multiply it. Now, what I will do is take this half, okay, minus j, okay, minus j by 2 delta f minus fc plus delta f plus fc signum of f. Okay. Same thing, minus j signum of f, half is already there. So, 1 minus j by 2 signum of f. Now, this I can write as 1 by 2j, okay, delta of f minus fc plus delta f plus fc signum of f. Now, when I multiply with signum of f, we should know what are the frequency components, whether it is positive frequency or negative frequency. So, this is a delta function which is existing at f is equal to fc, that is, this function is here. So, we have a delta function here, okay, existing. So, This has to be multiplied by a factor 1, because signum of f is 1 for all positive frequencies. So, I will get a 1 here. Then another frequency component is here, this is minus fc. Okay, here signum of f is, this has to be multiplied by a factor of minus 1. So, when I do this, I will get the answer like this, 1 by 2j delta, this does not change, whereas this becomes minus delta of f plus fc. If you look at these, this is a x cap of f. Now, when I take the inverse Fourier transform, that is this step, it is a famous notation, this is nothing but equal to sine 2 pi fct. Okay. So, this is just revise this a little. We have cos 2 pi fct, that is a given signal. Then we identify 3 steps in solving this. The first step is first calculate the Fourier transform of x of t, then multiply by minus j signum of f x of f, then use the third formula. When I do all this, I will got a sine 2 pi fct. Okay. So, this is the answer. Now, another question can be x of t can be sine 2 pi fct. Then when I calculate the Hilbert transform of it, I will get minus cos 2 pi fct. So, this is how you have to solve Hilbert transforms. Okay. Remember these 3 steps. These 3 steps can help you in solving any problem given Hilbert transform.